So if you're anything like us, then you probably like movies and superheroes. And you've probably seen this movie before.
And if you haven't, then where have you been?
Yeah, Thanos no longer requires our silence, guys.
If you have, then you'll be well aware of this scene.
So, I'd like to run one last sim before we pack it in for the night. This time in the shape of a mobius strip. Inverted, please.
Processing.
Right, give me the eigenvalue of that particle factoring in spectral decomp. That'll take a second.
Just a moment.
And don't worry if it doesn't pan out. I'm just kind of...
Model rendered.
As a general audience member, that sounds really fantastic. Like, wow, Tony Stark has invented time travel. But as mathematicians, we have to question, is the science and the maths behind his reasoning and his invention of it actually accurate? And that's what we're gonna try and understand today.
So the first thing to cover would be, what is a mobius strip?
I'm glad you asked. Here is one I made earlier. This wonderful thing here is a mobius strip. From the look of it, it doesn't look that incredible, but actually it has many properties that are quite interesting. And you can actually try out these properties yourselves. All you need is a piece of paper, a pen, and some scissors. You can make a mobius strip by taking a strip of paper, rotating one end 180 degrees, and then joining the ends together. One of the most interesting properties of a mobius strip is the fact that it's actually all one side. We can prove this by simply taking a pen and drawing along the middle of the surface.
As you can see, we've drawn one continuous line, proving that the mobius strip only has one side.
This property is actually really useful in real life. For example, machine belts use mobius strips because it means that they'll get equal wear and tear. If it was just a cylinder, then it would get a wear on just one side, whereas using a mobius strip, it gets wear and tear on the one continuous side that we've just proven to exist.
So what would happen if I cut down the middle of the mobius strip?
So, if you cut down the middle of a mobius strip, you end up with one single loop with several twists in it. Sadly, it's no longer a mobius strip anymore, but it's still quite interesting.
So what would happen if my cut is slightly off-centre?
So this time, if your cut isn't perfectly on the centre, then you get two interlinked loops.
One of which is a mobius strip.
So those are some properties, and it's all very interesting, and you can understand why they used it in the movie because it makes it sound fancy.
So you can make two different kinds of mobius strips, a left one or a right one, and this depends entirely on which way you twist it when you're making it.
So this is a left mobius strip and this is a right mobius strip. And as you can see, though they are similar, they're not identical. And there's no way for me to turn this mobius strip and make it look similar to this mobius strip. You can tell that they're different because if you look closely, this one is always behind no matter what I do, whereas this one is always on top no matter what I do. And so therefore they're different.
If we look at these two mobius strips, there's nothing that we can do to make them line up exactly, or at least nothing in 3D space. The only option is to take a mirror image of one. So this is called being chiral. These two mobius strips are enantiomorphs. So if an object has a line of symmetry, then it's achiral. So there are loads of different examples of enantiomorphs in real life. So your hands, or a pair of shoes. So if you look at my right and left hands, you can see that they're different. So if I put my right hand next to a mirror, the reflection is almost identical to what my left hand looks like normally, and vice versa. And so as a result, hands are enantiomorphs. So chirality shows up all the time in chemistry. There's lots of different crystals and molecules that form in either a left or right manner. Like we saw with the mobius strips before, if we want to make one, we need to take a strip of paper and turn it into a loop with a twist.
So are there any other shapes that you can make in that way which are similar to a mobius strip?
Yes, there's quite a few. Imagine we have a square of paper that can stretch and pass through itself without breaking. If we want to make a Mobius strip, we join these two red sides together so the arrows are pointing in the same direction. But if the arrows started in the same direction, then we just end up with a cylinder.
But what if we were to join the other two sides of the square as well?
So if we start with our square for a cylinder and make the other two sides pointing the same direction as each other, we'd end up with a torus or donut or a coffee cup. But if we switch the direction of the sides, it's slightly more difficult to visualize. So with this square, we'd end up with what's called a Klein bottle, which can't really be represented very well in our 3D world. So that's a self-intersection. But if we could perceive things in 4 dimensions, this would be a surface with only one face and no outside or inside. So as well as being a torus with a twist, you could also get this by gluing a left and a right Mobius strip together.
So you mentioned that we can't properly represent this in 3D space. So what would it look like in 4D space?
So in 3D space, as you can see, it passes through itself here and then comes out through the opening here. So in 4D space, this part would sort of go round to the side or sort of behind it and then through the opening without intersecting at all.
And here we have another version of a Klein bottle. It has the same properties, but this one instead was knitted and made by my nan. There is a knitting pattern for this, so if anyone wants
Link in
it,
the description.
down below. So we've made a Klein bottle, we've made a torus. What would happen if now on the square if we swapped the arrows the other way?
So this one's even weirder than a Klein bottle, and this makes the real projective plane, which also can't really be represented very well in 3D space without intersecting itself.
It's very complicated. Please look it up if you want to see what it looks like. So now that we've covered those 3, are there any others that you can make from that square?
Well, there's actually one more shape that we can make. If we instead make the edges share a corner rather than being opposite, then we can join them and turn them into a sphere. So a sphere, a torus, a Klein bottle, and the real projective plane are the fundamental polygons that can be generated by a parallelogram, or a wonky square. So now that we've covered all the maths, how accurate was Tony Stark when he was inventing time travel?
Well, one thing that they definitely got right was what a Mobius strip looked like. Friday definitely correctly displays a Mobius strip as the model. The concept of using a Mobius strip to model time is actually a valid idea. With the way the timeline is defined in the MCU, having a one-sided shape makes sense, as no matter where you travel on the Mobius strip from your starting point, logically you'd still be on the same side as where you started, and that means you should be able to get back to the original timeline with nothing changed, just by following the middle line.
Even though using a Mobius strip to model time has some logical sense, Tony says an inverted Mobius strip, which is less logical. We've seen that there's no way to invert a Mobius strip without just reflecting it in a mirror, in which case it's still a Mobius strip.
So realistically, Tony's statement is just a load of technobabble to make it sound impressive. As far as his breakthrough moment goes, it's maths to sound fancy, but you know, who knows? Now that the multiverse is broken open, you could use a fundamental polygon to model time instead of a Mobius strip, and maybe that's more accurate, but we will never know.
Who knows?
Because Tony's dead.
Thanks for watching us break down one of the biggest movies ever using maths.
I hope you all enjoyed it.